Okay, so welcome to the first seminar that we have in 2021, in fact, I think. So my name is Anna Mai, I'm the head of communication at ICMAB, and today I'm very happy to host this seminar. That it's the first one that we do from the Sala d'Actes Carles Miravilles since last year, nearly. But of course, it's also online, and probably will also be on YouTube after this. Well, the speaker is Claudio Cazorla, and I'm just introducing now Mariona Coll, that she will introduce the speaker. Okay, so thank you. If you have questions, remember that after the seminar, you can also do them asking in the chat or in the questions and answer icon. So yeah, have a nice seminar. Thank you.
Hi, good morning, everyone. With Ricardo, we are pleased to introduce you Dr. Claudio Cazorla as invited speaker in today's ICMAB seminar. Claudio performed his PhD thesis in computational physics at Universitat Politècnica de Catalunya. When he finished in 2006, he worked as postdoctoral researcher in several renowned institutions, such as the University College London in UK, and also here at ICMAB under the supervision of Max Stengel. In 2014, he was awarded with the prestigious ARC Future Fellowship at the University of New South Wales, Sydney, Australia. And last year, he got a Ramon y Cajal Fellowship and returned to the Universitat Politècnica de Catalunya. Claudio's primary research interests are the application and development of computational techniques to understand and design materials with potential for nanoelectronics and energy conversion harvesting applications. Today, he will talk about rational engineering of binary oxides and semiconductors for photocatalytic applications. So, Claudio, whenever you are ready, the stage is yours.
Yeah, thank you. Okay, thanks thanks to Ricardo and Mariona for inviting me to give this seminar. I have to say, so I'm going to talk about, as Mariana said, about this rational engineering of binary oxides for photocatalytic applications, in particular for water splitting reaction. But before moving into the actual content of my talk, I would like to say that I'm not new, as Mariana has mentioned already, but just to explain that I'm not new to ICMAB. So I was here from 2010 to 2014 under the supervision of ICRIA professor, Maximiliano Stengel, and I worked with him in ferroelectrics and multiferroics by using DFT techniques. I learned a lot under his supervision, and I really am grateful to him. So after that, I moved to Australia, where I continue working on these ferroelectrics and multiferroics materials, but at the same time, through many collaborations with experimentalist colleagues, I expand my portfolio of materials. So now, to this day, I'm kind of like a semi-expert or expert also in the study of fast semiconductor materials for electrochemical applications, like, for instance, solid-state batteries, or I'm interested in the characterization of phase transitions on these materials. And another family of materials I've been working in recently, and about which I'm going to be talking today, it's photocatalysts and electrocatalysts, right? So since last year, I'm back to the Politècnica University of Catalonia, which is the institution where I got my PhD. So I'm a Ramon y Cajal Fellow, and if any of you are interested in my research and want to contact for whatever reason, so you can always just go to my website and retrieve all the necessary information. It would be a pleasure for me to talk with any of you. I'm based in Barcelona, so it's relatively easy for me to come here and discuss about whatever, right? So after this bit of publicity, I'm going to start with the seminar itself, right? So first of all, I'm going to start by the end of the talk. So I'm going to start with the acknowledgements. So I'm going to be talking about two recent works on these materials, which I've been doing, or I've done in collaboration with Professor Ricardo Grau Crespo from the University of Reading in UK. and also from my Chinese colleague Zhao Liu from Sun Yat-sen University, who is a fantastic researcher, right? So the results I'm going to be talking about were produced during my stage at the University of New South Wales in Australia, so that's where all these Australian funding agencies appear here, right? So let's start. So I guess I don't have to convince anyone about how much we like energy. So we use enormous amounts of energy for power on our devices, for comfort, for transportation. However, also I guess I don't have to convince anyone that the ways we've been producing energy so far has not been fully friendly with the environment and not sustainable, right? So as you may know, there is a lot of research going on in trying to transition from the traditional sources of energy, like can be fossil fuels, to some other sources of clean energy, right? One of such possibilities, or one of the possible fuels we can be using in the future, which are respectful with the environment, is hydrogen. So essentially, we can take energy from the sun in order to produce electricity that then is employed to make electrolysis. So that's only by means of electricity to split the water molecule. So we can produce hydrogen that later we can storage in tanks, and we can export to overseas or within our country, so that later we can just use in combustion hydrogen engines or fuel cells for domestic industrial use, right? So as you may know, hydrogen is a fuel that, as a result of combustion, only produces water and oxygen. Sorry, so it's not really it's really respectful with the environment. The thing is that we will need, in principle, huge amounts of hydrogen in order to rely on that technology, right? And water electrolysis, which is the typical process by which we produce hydrogen nowadays, it has some shortcomings in terms of the energy efficiency, so it's not energy very efficient, right? And also it requires from water, sweet water? Oh, sweet water? No, from unsalted water. Okay, so it may use water that it's used for drinking, which is not an abundant resource in the world, right? So there is a kind of problem with the ways we produce hydrogen nowadays. And one possible solution to overcome these limitations, or to contribute to this production without relying too much into electrolysis, is to use crystal materials in order to split the water molecule directly by means of using sunlight, right? So there is no any electricity involved here. So essentially, we have a material in which, at some part of its surface, some some water molecules absorb. And if we have a material which is able to transfer some holes or take some electrons from those water molecules in order to produce this, to induce this oxygen evolution reaction, in which we break it down in terms of in the form of molecular oxygen and protons, right? And then those protons, right, goes and absorb on other regions of the photocatalyst. And in that case, the same material is able to transfer electrons, so that now we can produce from these protons, we can just form the hydrogen molecule, which is our final goal, right? So if we are able to do this in materials, right, in crystals, right, we have a very clean and efficient way of producing hydrogen, right? Of course, the way we can have these holes and electrons going from one side to the other is by producing them through sunlight, right? So if we have a material which absorbs sunlight within the ultraviolet and visible spectrum, we may have a large production of these pairs, of these excitons, right? And therefore, we can feed up these couple these two reactions, right? in a more physical way, or from a more physical perspective, which are one of the main characteristics that a photocatalyst material needs to fulfill. Okay, so first of all, the energy bandgap, the optical energy bandgap of the material has to be somewhat around 2 to 3 electron volts in order to absorb, in an efficient way, sunlight, right? So to all the energy containing sunlight to use it. And then also we need that the band alignments, so the positions of the top of the valence band and the bottom of the conduction band, they have to be above and below the potential of the two corresponding reactions. So in particular, the edge of the valence bands has to be below, slightly below, the potential corresponding to this oxygen evolution reaction, whereas the conduction band edge has to be a little above, between ideally around 1 electron volt, above the potential for the hydrogen reduction reaction, right? So these are 3 conditions that are easy to estimate because they are Bohr-like, right? Of course, there are many other aspects that in practice are very important, right? Like, for instance, the recombination time between these electron and holes, etc. But those aspects sometimes are better controlled by the morphology or nanosynthesis, right? In this case, however, this is something that may very well be described by the bulk system itself, right? So this is very briefly how a photocatalyst, for the particular case of production of water out of hydrogen, out of water and sunlight, should work, right? And which are the main physical characteristics may fulfill, right? So we already know a lot of many of these photocatalyst materials, right? And here there are some examples which are quite well known for anyone working in this field. The problem, as always, as in any materials field, is that it doesn't exist the perfect material, right, in order to conduct this hydrogen production. For instance, we have this material here, which has a nice energy bandgap, 2.1, which is very appropriate for this water splitting reaction. And also the band alignments of it are quite well placed, right? So not too far from these 2 lines here, which mark the potential of the two reactions which are involved, right? However, this material is made of tantalum, which is a very expensive element because it's very scarce. So we cannot really make too much with this kind of materials, right? On the other hand, we have other materials which are much more abundant in the Earth, like, for instance, the zinc oxide. But in this case, the energy bandgap is too large, and also the band alignments are not optimal, right? Because this top of the valence band is just too below the potential corresponding to the oxygen evolution reaction. So the motivation of the main motivation of the 2 studies I'm going to present next was, okay, so can we systematically design enhanced photocatalytic materials? And here the key word is systematically. Of course, I mean, we can, if I was a chemist, probably my approach will be more into the synthesis of new materials, right? However, this motivation in this case was more like physical related, so to say, in the sense that now our target probably is less ambitious, is, okay, let's go to these materials, or some of these materials, which we know that they are already good, but they are not perfect. And let's see if by doing something on them, right, we can just make them perfect, right? So no new materials, just no materials, but doing something else on them in order to improve their photocatalytic performance, right? And of course, we want to do that in a systematic and predictive way, yeah? So with this motivation in mind, I had some drinks. Well, no. What I did was to think about 2 different strategies, right? So one strategy, it's about mixing. So we have 2 materials with different properties. None of them is perfect, but they fulfill some of the 3 or 4 necessary requirements, right? We mix them and we wish for the best and hope that the mixed material will be some hybrid between the two and will be much closer to perfection, right? So this is one strategy I'm going to be talking about. I'm going to show some results. And the other strategy is stretching, right? So as you may know very well, probably much better than me, when we apply stresses in materials, we can very well change their physical, chemical, photocatalytic properties. The question is, so can we do this with some kind of level of prediction and of systematic knowledge? And this is what I'm going to be talking about today. And I'm going to try to convince you that, in fact, these two strategies, both of them, can be quite successful in finding, in improving the photocatalytic properties of already known materials, right? Of already known photocatalytic materials. Okay, so I've already explained the motivation for my work. I've already explained in what consists the water splitting reaction by means of photocatalyst materials. Now I'm going to just give you very short description about the methods I've been using in these works I'm going to be talking about, right? So I'm a materials computational scientist, and what I do basically is to use density functional theory approach in order to study materials. Density functional theory is a kind of first principles method, which means that with this method, we are able to find out the ground state properties of the electrons in a crystal, right? Without making fundamental assumptions on the interactions between those electrons, right? So DFT is not the only kind of first principles method, even though it's very common in material science. And the reason for that is that there are other first principles methods which actually are much more accurate than DFT, but also more complex, like can be couple cluster or quantum Monte Carlo. However, in those approaches, typically, people deal with many body weight functions, right? So they actually have to deal explicitly with a function which is extremely complex and which depends on 3 by n, where n is the number of electrons in the system, this number of variables, which is a tremendously complex magnitude, right? On the other hand, in DFT, we have a simplification, a significant simplification, because in DFT, we deal with electronic densities, right? So now we go, rather than a function that depends on the 3 to the 3 per n degrees of freedoms, now we only have a function that depends on 3 degrees of freedoms, x, y, and z, which means the spatial position in the crystal, right? In practice, what we do in DFT is to define an energy functional for which we know rigorously that the solution is unique and it corresponds to the true ground state of the electrons, right? How we get that solution, so we need to do some kind of numerical or theoretical mapping of the real many electron interacting system to a system of mean file-like of non-interacting electrons, right? Which are known as the Kohn-Sham equations. And we need to solve and the typical way of solving those equations is in an iterative fashion, right? And we have different terms in the Hamiltonian. We have a kinetic term, an external potential, a Hartree term, which is nothing else but the Coulomb energy that an electron in a position feels as a result of the other electrons. And then we have some term which is called exchange correlation energy, in which we put all the things that has to do with the quantum nature of the electrons, as for instance the exchange energy and also other correlations, right? That has to a quantum mechanical origin. And that typically we don't know what form it has, and therefore we need to approximate in practice, right? So when people doing DFT talks about different flavors or different versions of DFT, basically we are talking about which approximation I'm using for this term here, right? Which come into this equation that I have to solve iteratively until my electronic density is properly converged, okay? That's the only technical description I'm going to give during my talk. But for the work related to strategy one, which is about mixing, the kind of DFT calculations based on these particular approximations, so PVE and PV-sol, and also some hybrid functional potentials, what I'm going to be doing basically is band alignments calculations, configurational free energies calculations, and vibrational free energy calculations. So I'm going to deal directly with temperature, which is something that most of the time we don't see in this kind of first principles works. And for the second approach, the one that is related to stretching, my simulations are going to be of the type of bulk strain relaxations, in which we impose some strain in some particular directions, and also the electric tensor calculations as well. Okay? Okay, let's go into the content, the physical, chemical content of the talk now. And we're going to be talking about strategy one, which is about mixing. So this work, which was published recently and in this journal, so was motivated by some results already known for gallium phosphide and zinc sulfide. So these are very well-known materials, semiconductor materials. Their structure is very well-known. Everything is very well-known. And the thing is that by separate, these two materials are not really good in terms of photocatalytic activity, right? They have some good attributes, but not all of them are good, right? So for instance, gallium phosphide is a very expensive material because gallium is not abundant, so it's rare and it's expensive. And also the band gap, even though its magnitude is not large, it's 2.2 or around 2.3, it seems to be that the band gap is indirect, right? So that's not optimum data for the absorption of photons, right? On the other hand, zinc sulfide is cheap. It has a direct band gap, but the size of its band gap is too large, right? It's just beyond 3 electron volts. So there were some old experimental works saying that when you mix these two guys, their energy band gap properties are kind of like favorable for photocatalysts, even though in those old works there was nothing related to photocatalysis. So our question was, okay, so it's possible that these solid solutions between gallium phosphide and zinc sulfide are good photocatalyst materials for this water splitting reaction? Okay, so this is what was our initial motivation. But of course, one problem that I guess every experimentalist experience in the lab is that you cannot just mix everything, right? So when we do simulations, we mix everything and we don't care about whether it's really happening or not in reality or not all the time. So the first question we wanted to address is, okay, so when we mix these two guys, it's the product really stable against the mixing into the pure gallium phosphide and zinc sulfide materials? And for doing that, what we did is to just go to the very simple thermodynamics and statistical mechanics basics and have to calculate the mixing Gibbs free energy of the solid solutions, right? So basically, we define this mixing Gibbs free energy as the difference in free energy as a function of composition and temperature with respect to the two materials when they are unmixed, right? So in order for a mix temperature T and composition X to be thermodynamically stable, right, this energy has to be negative, and not only that, its curvature has to be negative. It has to be convex rather than concave, right? This has to do with the requirements on the chemical potentials, right, of a solid solution mixture. Okay, so this is something that we can calculate with some approximation, of course. We apply approximations, but which, as I'm gonna show you, gave us a quite realistic view of this system. So how to do that? How to calculate these mixing free energies, right? So how to calculate basically this term here, which depend on temperature and on composition. So what we do, or one possible way of doing that, is to take a large supercell and just put the atoms for a given composition in all possible positions, right? So we generate a large ensemble of configurations and we calculate the energy for them, right? And just applying very simple statistical mechanics concepts, we can estimate the partition function. Therefore, we can estimate the free energies at zero pressure, for instance. And then even we can estimate, by defining this thermal Maxwell-Boltzmann probability, we can estimate average values of operators or of quantities, right? Like can be energy bandgap, like can be any other thing. The problem with this approach, in principle, if you have infinite computer power, you can do that just by running a large number of simulations. However, this is, in practice, is quite difficult because this approach of supercell analysis, it has a very dramatic size effects. So that means that you have to really go to really large systems in order to make sure that your results are meaningful. And as you may just do a simple exercise of looking at the number of permutations in a supercell, right? That is a number that grows exponentially with the size of the supercell, right? So in principle, just by pure brute force, it's not possible to do this kind of free energy calculations, mixing calculations in a good way, in an accurate way. However, because we are dealing with crystals and crystals have some periodicity, of course, we can do some tricks and exploit, for instance, crystal symmetry, right? So that means that we generate all possible configurations for a given composition in our supercell, but by using symmetry relations, we know that many of those configurations in reality are the same, right? So they have to give lead you to the same energy, right? So by applying this crystal symmetry, a problem that may involve, for instance, a number of calculations of the order of thousands. If you select a highly symmetric system, then it can be reduced to a problem of calculating over 100 different configurations, and therefore is computationally affordable. And this is what we did. We use a specific software which basically does this, right? To make all the symmetry analysis and reduce the number of all possible configurations to just few of them, which are the irreducible ones. Also, we were interested in seeing how was the contribution of the vibrational properties of the solid solutions to these mixing free energies, right? And this is something that it's not seen everywhere because normally it is said that the configurational part is much more dominant, right? So we just wanted to see whether that's really true, was true also in this case. So we also look at the vibrational free energy to see how important it was. Okay, results. So we consider the solid solutions, right, in the zinc blend and bauxite structure, which are the two polymorphs that are observed for this gallium phosphide and zinc sulfide. And we were able to estimate the mixing free energy for the solid solutions as a function of gallium phosphide content and also temperature, right? They look pretty much similar, right? So there are not very large differences between the two polymorphs, which is it makes things easier. What I show here is just like a temperature cut of the at 300 Kelvin and at 1000 Kelvin, right? Of this zinc blend and bauxite solid solution, right? And what we find out is that from all compositions, 25%, 50%, and 75% look like they were kind of like pretty much stable, or at least stable at room temperature, right? So this difference of energy here, it's a few millielectron volts per formula unit. And as you can see, even though that they are not negative, which was one of the conditions I said before, it's pretty much close to zero, right? Also, the shape of these curves here, it's the right one, so it's a concave, convex, not concave shape, right? And in any case, when you go up to 1000 kelvins, right, which is, I guess, is what normally you do when you synthesize these materials, you go to high temperatures. At high temperatures, the configurational entropy is so large that mostly all possible compositions are stable, right, or few of them are fully stable. So, in other words, what we conclude from this first set of calculations was that 25%, 50%, and 75% were good candidates materials, or solid solution materials, right, in order to start looking at the photocatalytic properties, right, because they were quite likely to be made stable or stable, almost stable in reality, in practice. Yeah. So one thing we look at was at the energy bandgap, right? So how the energy bandgap changed with temperature, right? So here is a plot, for instance, that for a fixed composition in which we calculate the energy bandgap, right? The energy bandgap for all the configurations that we have generated that are irreducible, right? All, so even though there is a small number of calculations done here, right? How big is this? It has to do with the degeneracy of each of those irreducible configurations. Even though it's relatively small number of calculations, we have a lot of information here, right? Much more information, or the same information that if we had performed thousands and thousands of calculations, right? Just because we did the symmetry analysis, right? Okay, so what we found out is that within the ensemble that we calculated, there was a large dispersion on the energy bandgap, right? So it's quite surprising, right? So this guy here is a guy which at 0 temperature is the ground state, but mostly all of other configurations, has a much smaller energy bandgap. What does it mean? This means that just considering configurational effects, when you now calculate the energy bandgap of these materials as a function of temperature, right, you have that the energy bandgap, and again, I'm neglecting any electron phono or any vibrational effect here, right? Just configurational effects, right? We have that with temperature, this energy bandgap tends to decrease, which is something that, in principle, since they are already within the interval of the 2 to 3 electron volts, right, which seems to be a very nice or positive result, right, because these 3 compositions that we decide they were kind of like stable in reality, also they fulfill the right magnitude for the energy bandgap. Not only this, we also find out by looking at the electronic band structure that these energy bandgaps were direct, right? So they were just kind of luckily inheriting the direct bandgap from the zinc sulfide, right? And on the other hand, they were inheriting the small bandgap from the gallium phosphide. Yeah. Well, we also did the calculation for the band alignments. So this is kind of like advanced calculations one can do, but it's feasible, right? So of course, this is just done for one or few configurations. But what we found out that it was that for these 3 compositions, which actually had an appropriate energy bandgap size, they also had a kind of appropriate band alignment, right? In particular, this 25% content of gallium phosphide, it's quite promising from a practical point of view, because it's the one with the smaller content of gallium phosphide, which is the expensive one, let's say. And in this case, again, the energy bandgap is right, it's around 2.7, 2.8, and also the band alignments looks kind of pretty appropriate, right? Pretty convenient, right? Which is just of the order of 1 electron volt, 1 point something above and below these 2 potential lines here, right? So, first partial conclusion: mixing different materials which are not perfect but which are kind of like good, it may result in an improved photocatalytic material, right? There is no need to go to new ones. We can just mix the ones that we know, in some cases, of course. And we can, or at least we can do the study with theory, and we can then propose to experimentalists whether it's useful or not for them to go ahead with the experiments. Okay, let's move to the second strategy, stretching, right? And I have to say this is something that I very much learned for the first time here at the ICMAB when I was a postdoc, right? So as you know, in thin films, we can change the functional properties of materials by taking advantage of the change in the atomic distances, right? When you grow the system experience with respect to bulk, when you bulk a thin film, right, which is mechanically coupled with a substrate, right? In other words, a system that bulk has some lattice parameters. When you grow it on top of a substrate, right, you can very much change the structure, and therefore you can change the magnetic, ferroelectric, any kind of functional properties, right? So this is something that has been extensively explored in the community of ferroelectrics, multiferroics, but not so much in the photocatalytic community, right? And this was some question we wanted to know. Is it possible to change in a kind of like reasonable and systematic way the photocatalytic properties of known materials again by doing this kind of already known approach, synthesis approach? Okay, so what we did was to start by the archetypal material which is used in catalysis, which is ceria, so cerium dioxide, right? And basically we did the study of its properties under epitaxial strains. So we took it, so what we do is in the simulations, all this is theoretical results, we applied some kind of epitaxial strain or biaxial stress in the 1-1-1 direction, right? Or in the 1-1 plane, sorry. Yep. So what happens when you apply this epitaxial strain? Essentially, we have a tensile epitaxial strain on the right, which means that you are making the in-plane parameters larger. So if you look at the bonds, right? So if we take a cerium atom and we look at the oxygens around it, all those bonds which has some large projection on the plane over which we are applying a strain, they will increase, those bonds, they will increase on the tensile side, right? Whereas they will decrease on the compressive side, right? So see, this is the CO2, right? So CO2 is this kind of bonds which has a large projection on the Y1 plane. So these guys increase on here and decrease on this other side, whereas the cerium O1, which is the bond which is out of plane, right? It has the opposite, normally it has the opposite behavior. So when you compress the system, it goes up on the out of plane direction. So this bond starts increasing, whereas on the tensile side, this type of bond decreases. Nevertheless, when you do the average, what happens is that in average, when you go to tensile stresses, epitaxial strain, you increase in average the bonds, the distances between this ceria atom and the oxygen atoms around it, and the opposite when you go to compressive strains, right? So what happens when you do this on cerium dioxide on the 1-1 plane? What happens with the energy band gap? Well, the energy band gap, it's this curve here, this point here, right? And we see that something that when it's not stressed, we have an energy band gap of 3.2, which is a bit too large, right? However, when we go to the tensile stress side, the energy band gap starts to decrease, and at some point, around 2.2% of epitaxial strain, the energy band gap starts being appropriate for this kind of like absorption of photons, of sunlight photons, right? Whereas when you go to the compressive side, what happens is the energy band gap starts increasing, right? So if we were to propose what to do for experiments will be to apply some tensile stress, right? Not only this, we also look at the variation of the band alignments with respect to when you apply this epitaxial strain. And we found out that under tensile strain, in fact, the band alignments starts placing in a kind of appropriate way, right? Even though, as I will tell you later, we were not able to find out a quite systematic trend for the band alignments. Not so for the energy band gap. Well, I'm not going to go into details now, but also, of course, we are able to look at the electronic density of the states. So how the electronic properties of the material change when we apply this epitaxial strain. As a main characteristics of the materials I'm going to show now is that on the valence band, on the top of the valence band, we have an overlapping between the p orbitals from the oxygen and the d orbitals from the for the f in this case, the f orbitals from the cerium atoms, right? It's dominant the oxygen portion on the valence band, whereas on the bottom of the conduction band we have some kind of similar overlapping. However, now the component of f orbitals from the cerium atoms is much larger, right? So we know which is the nature of the electronic orbitals at these points, which are the relevant ones for, marking these band alignments. Okay, so what else? So question is, if we take exactly the same material, but now we apply epitaxial strain in another plane, not just in the 111, because we have many other planes or many other possibilities, what happens to the same properties? Do they react the same? The answer is no. So if we take the same material, but now we apply the stress in the 001 plane rather than in the 111, we have a qualitatively similar solution, which is that on the tensile strain side, the energy band gap is reduced to values which seems to be appropriate, right? However, in this case now on the compressive side, we don't have any large variation on the energy band gap, in contrast to what we found for the 111 plane, right? So this seems quite funny, no? So there is something else. I mean, it's not just intrinsic to the material. It depends on how you apply that epitaxial strain, that the properties may be changed in a direction or in another, or in a percentage or in another, right? I'll come back to this in a few moments. We did the same for anatase titanium dioxide, which again is a very well-known material in the field of photocatalysis and catalysis. And we did the equivalent study, so we look at the structural changes and also at the optoelectronic changes that experience under epitaxial strain, in this case in the 001 surface or plane, right? In this case, we had that now the change of the energy band gap was quite linear, right, through the whole interval of epitaxial strains that we investigated, which is quite large. I have to say, in practice, it probably is not possible to apply such large epitaxial strains, of course, but we were more interested also in finding the fundamental reasons for these behaviors, right? So what's different from what we saw for cerium dioxide, and now also the band alignments, they had like an opposite or very dissimilar behavior, right? So here, as well as for the energy band gap, we see a kind of like systematic, steady behavior. For the band alignments, that's not the case. So here it stays constant, then decreases, then constant again. On here, it doesn't change too much. So difficult to predict, or at least, or even to identify any systematic trend on the band alignments, not so for the energy band gaps. What else? So we took a third material just to have a larger database set from which to draw conclusions, right? So we also look at zinc oxide, which is also quite famous material, right? In this case, the structural parameters are different. So there is one kind, this bond here, funnily enough, when you go to the compressive side, to the tensile side, it increases rather than decreasing. So there is some kind of like funny structural behavior going on here. And also the energy band gap in this case, for all epitaxial strains, they were below the 3 electron volts. But now the tendency was totally opposite to what we saw before for titanium dioxide and cerium dioxide, which is that now it decreases for both polymorphs. It decreases when you go to the compressive side rather than when you go to the tensile side, right? So we demonstrated that, in fact, when you apply epitaxial strain, these optoelectronic properties, which can be beneficial for photocatalytic processes, the changes are significant. The reason now, or the next thing to answer is, okay, so are we able to understand why is it happening? Can we predict them? We do really understand them, because otherwise there is not really too much sense, no, in doing this, right? As you can see, again, I mentioned there is a quite large difference in the behavior of the energy band gap. So now I'm going to focus on the energy band gap, because we were not able to really find any systematics on the band alignments, right? And also to simplify the analysis, right? So now I'm going to focus on the energy band gap. So the same material, but applying the stress in different planes, it changes, it presents a completely different reaction from the system. And when you compare different materials, the trends can be totally different, right? So can we understand this somehow? Okay. The typical response or the typical theory that was had been used before in order to explain these changes in the energy bandgap, which are just here, right? So this is now, this table summarizes the results for maximum tensile stress, biaxial stress, minimum or maximum compressive biaxial stress. This is the change, relative change on the energy bandgap, right? So as I say, so before us, people were trying to understand these changes as a function of, or in terms of the deformation potential theory, which basically have to do with how the overlapping between the oxygens, the p orbitals, and the d or f orbitals from the transition metals, how they are affected by changing the structure by applying stress, right? So essentially, on that theory, what happens is that when you put the atoms closer, right, somehow you are increasing the overlapping between these H orbitals, right? And that's what happens, what the expected result will be to increase the energy bandgap because you are somehow increasing the crystal field, right? So you are making this bonding anti-bonding difference larger, right? On the other hand, when you decrease, you decrease the overlapping between those orbitals, oxygen and transition metal orbitals, you were decreasing, weakening the crystal field, and therefore the energy bandgap had to close, right? So this is the naive understanding that we had, that had been explained in previous articles to us, right? However, if you look now, if you look not just to one material, so you look at different cases, you see that there are some problems here, right? And are the following ones. So here I plot how the distances, the average distances between the oxygens and the transition metals change as a function of material, as a function of epitaxial stress, right? And we can see that it's always pretty much the same. So on the compressive side, tensile side, sorry, you know, we have a larger or a smaller variation, but it increases, whereas on here it decreases, right? However, this is, in other words, the structural properties of how you change the distances between the atoms. Of course, it will depend on the mechanical properties of the material, the elastic properties, but always you will end up having, or most of the time, having an increase of the distances on the tensile side and a decrease of the interatomic distances of relevance on the compressive side. However, that's not reflected on how the energy bandgaps change, right? So for instance, we have here that, you know, the same material and the same tensile stress, it has a very kind of similar deformation with respect to the unstrained case. However, the effect on the energy bandgap is much more larger here. It's a factor of 7 almost here, or, you know, from you know, the same material. So when you apply the stress in a surface or in another, right? So and the same way. So here we have now we compare two different materials, but we have a kind of like very large expansion, right, of the bonds of relevance. Here, a very small one. However, if we look at the response of the materials here, despite this is quite large, small, sorry, because the system is quite stiff from a mechanical point of view, right? The change in the energy bandgap is huge, whereas here we have a huge structural change, and the change in the energy bandgap is just small, right? So there seems to be some piece missing here, right? And this is what we try to find out. What are we missing, right? So as I said before, so we didn't say anything new, but we just look into the literature, and we found out that, of course, there is not only one way to change the energy bandgap, which is given by this deformation potential theory, which is mainly based on stress, or if you want, on a strain, which is what I've called this delta D divided by D, so how the distances between atoms changes. But also, there are other ways that has to do with electronic screening, right, on the material that also may have a strong effect on the energy bandgap. In particular, by shortening the atomic distances or weakening the dielectric screening, the crystal field is enhanced, and as a result, the bandgap is widened. And conversely, by increasing the bond length or enhancing the dielectric screening, the crystal field is depleted and the bandgap is reduced, right? So I would say that so far, people in the field had just taken into account this contribution, but this other part here, which has to do with the many electron, the electric screenings, which is something that acts more in the medium and long range, right, had been pretty much overlooked, right? So what we did was to consider a very simple model, right, analytical model, in which we assume that the energy band gap could be changed by two different sources, by changing the stress, or if you want, the distances between the atoms, and by changing the electric properties of the material, right? Of course, this is a very, this is not a realistic or exact model, right? Because, for instance, the reason why we write this product here is because we are somehow considering that these two guys are independent, where in reality that's not true, right? So this guy may have some dependence on this and the other way around. But just for having some kind of like meaningful, physically meaningful model, we assume this function here. And this has a very good, from the mathematical point of view, has a nice property, and is that when you consider, you estimate this change variation, relative variation of the band gap divided by the band gap of the material when it's unstrained, it gives you a nice contribution in two different terms, one coming from the change on the structural properties, and the other one coming from the electronic screening, right? And we can see that the factors that accompany each of these terms are pretty much similar, right? So it may happen after, it may be possible after looking at this form here, that these guys may be equally important or not for a given material, right? But importantly, or from an intuitive point of view, just the message to take away home is that in principle, there is not only short-range contributions to the variation of the energy band gap, which come from the from varying the overlapping between the orbitals, right? It may happen also that the energy band gap, it may be changed efficiently by changing other long-range or middle-range interactions that has to do more with the electronic screening in the material, right? And since we are working with oxide materials, we know very well that this term here could be non-negligible, right? So, okay, so taking this model, we came back to our results, right? So we had something that it didn't look systematic because, as I said before, these changes are very systematic, whereas these others are not. And now, by considering this simple model here and by making calculations also of the dielectric tensor of the material, we find out that the prediction, because this gives you a number, right, of our model, right, just by looking at the structural and the dielectric properties of the field films, right, they very well, or not qualitatively, but not quantitatively, but qualitatively, they reproduced the trends observed from the realistic or accurate DFT results. For instance, here we can see that for the same material, right, even though these numbers are not exactly the same than these ones, we have that, the order of magnitudes are similar, and also the tendency, right, of positive, negative, and how more or less different are these numbers, right? As I say, this is not perfect because, for instance, in this case, which the changes are small anyway, we have something with the wrong sign, right? But I would say that, it's kind of like, it can give you a very nice interpretation of why these changes happen, right? And for that, let's just have a look at some examples, right? So if you remember, if we look at the change on the energy band gap for a large tensile strain, we had a very small change in the energy band gap, even though the changes on the structural parameters, or if you want, on the overlapping between the orbitals, oxygen and transition metal orbitals, was quite large, right? And the reason for that is that, on the other hand, the other term here, the one that has to do with the electric screening, it has a different, an opposite sign, right, than the contribution from the short-range interaction, right? And these two guys, when you take into account this contribution from the electric screening, then you get something that is quite small, right? A negative. So still, this is dominant, but is not alone, right? What else? In this other case, in the same material but in a different plane, we had that this presented the largest change in the energy bandgap under tensile stress, right? Biaxial stress. And in this case, this guy was large, but if we look at the changes under the electric screening properties, we find out that in this case, also the sign in this case is the same than here. So you have two contributions that they sum up one with the other. They don't go into opposite directions, right? And that's the reason why we have such a large variation in the energy bandgap here, right? So another important thing to mention is that if the changes on the structural parameters are quite systematic, you always have these positives, these negatives. On the other hand, on the electric properties, that's not the case. It's very much materials depending and very much the actual strain depending, right? And this non-systematicity, together with this systematicity or this regular pattern on the other term here, give you at the end of the day this kind of what to this point was not systematic, but that now we think we can understand better, right? Trend, right? So as a conclusion, as a takeaway message again is that we can understand changes in the energy bandgap, not just based on local or orbital overlapping arguments. We also need to take into account, especially for oxide materials, the changes on the electric properties of the crystal, right? Which may be quite large when you apply any kind of stress. Okay, so conclusions from this strategy, second strategy of stretching is that it can be very useful, and I think we now have some kind of simple but meaningful understanding of how we can expect the material to change. Okay, so thanks for your attention. So I'm gonna stop here.
Thanks for the presentation, for the answers to the questions. Thanks to all our Zoom friends for the lively discussion. So maybe we call it a day, and we thank again Claudio for a nice presentation, and I see you another time. I guess the talk, if you are interested in reliving it, will be posted on our YouTube channel within a couple of days. Okay, thank you.
Thank you, thanks to all. Thank you.